So, so I'm presenting today. This is a paper from CVPR 2018. I'm gonna be on. Very informal. Ask questions at any time. This is more of like actually kind of like a story of how this paper came about. All right, so this work was done with Daryl Halle. So Daryl he was actually a junior at Villanova, and I brought him over the summer. We went to Los Alamos together. When I told people this, it is kind of weird though. It's like, hey, you want to come with me? He said, yeah. Do you want to live together? It's kind of weird. But we worked it out. Went to Los Alamos. It's a nice place. Santa Fe. If you haven't been there, I thought like we worry about scorpions and that sort of stuff, but just rattlesnakes. And so he's currently a second year PhD student now at UNC. We work together with Garrett Kenyon. Garrett is a scientist at Los Alamos, and it was just sort of a coincidence that we worked together. So I got this. It was a Department of Energy (DOE) visiting faculty scholarship thing to visit Lionel, and they said, "Well, you need to pick a host." I didn't know anyone there, so I just looked at. So every year they have the students come in and they do posters at the end of the year. So I looked at all the different posters and the titles of the posters, and there was so at Lionel it's mostly physics, and so I looked at all the posters, and there's one that said like deep learning, blah blah blah. All right, who's this guy, Garrett Kenyon? So I called him up on the phone. I was like, hey, I got this thing. Can I work with you? He's like, yeah, sure. Come on in. And then turns out he despises deep learning altogether. So it was a very interesting collaboration. Okay, so I want to just talk about like when I first came in, what I was planning on doing, and then actually sort of and just what happened. Okay, so this was my original summer project. If you're not familiar with this, it's a good paper to read. It's called the visual question answering paper. So I think this was ICCB 2015. But so the problem was we have an image, and then we generate a question, something like look at this image, and the question generated is how many horses are in this image, and this network is supposed to analyze both the image and the question, and then somehow spit out an answer. And so back in the day, this is actually pretty innovative, where they passed the image through a convolutional neural network, CNN. They passed the language through this recurrent network, this LSTM. And then what they did was at the end of each of these sort of individual streams modalities, you have a vector. It's a 1024 dimensional vector. And then all they do here is they pointwise multiply them together into this joint embedding. And then, so the idea was this joint embedding holds both the information of the image and the question, and then you just pass it through some fully connected layers to a softmax, and out magically comes the answer. And so this was really interesting. And what I wanted to focus on was like, well, why are you doing this pointwise? Like, how do you get a joint embedding between different modalities? All they're doing is multiplying these vectors together. Is there a better way to do this embedding? And people have explored, addition. You can do like outer product. So people have done a whole bunch of different things nowadays to do these joint embeddings. But at the time, I was like, well, maybe we can explore this a little bit better. So I brought this up to to Garrett, like, this is what they're doing, the VQA paper. Can we, maybe spend the summer looking at this? He said, yeah, you can do that if you want, but what I want you to do, my idea is scrap this whole thing altogether. So forget about deep learning and how they're doing all this stuff. Why don't we just do the whole gamut? Like, look at how you're doing perception, how you're doing language, and how you're doing the joint embedding. So the first idea was, okay, let's look at this whole multimodal learning problem with a different perspective. And he's all about like biological plausibility and neuroscience. He is a neuroscientist. So, and at the time, I had a newborn and I had a 5-year-old daughter, and she was just starting to learn how to read. And so I was like, okay, let's look at this whole multimodal learning problem with the perspective of different neuroscience techniques like sparsity, lateral inhibition, top-down feedback, and let's do it in the problem of reading children's books. So these are inherently multimodal. You have images, you have text, you have language, and I don't know, you guys probably don't know this, but there's like a new set of books on iPads and tablets and stuff that basically just they read. So they have the mode, you can read it on the tablet, or it reads to you. It's called read to me mode, right? And as it reads, it highlights the words in the book. And so I was like, oh man, this is like a great source of training data, because it's highlighting the word as it reads, that sort of thing. And then also what was really interesting to me in sort of the child development side was like, so my daughter, she couldn't quite read yet, but we had read these books over and over again, so she had completely memorized all the words. So if she would flip the pages, she would say the words that she's memorized, and it looks like she's reading, but she's actually not. So the idea was, well, let's just train. Can we train a system just to read children's books? So Daryl, he was more of a natural language processing guy. So he did this whole thing where he got like nouns and verbs and adjectives and all this, put them all on a list, and then sort of generated a bunch of just random sentences. So like the horse is green, look, green horse, blah blah blah, all this stuff. And then what we did was we took the sentences and we generated language, audio, through what's called Amazon Halle, which is just a text-to-speech engine that you can just push words through. And of course, you can have different types of speakers, and because we're sort of teaching a computer, we had to make it a child's voice. So this was the idea, and what we did was we put it through this architecture, which I'll describe a little bit more later. But the basic idea was, well, first of all, the way that we represent language in machine learning is typically through these things called one-hot vectors, where you have sort of your vocabulary in it. The word, to represent a word, you would just sort of put one in the vocabulary at the index of that position, whereas we're saying, well, really how we represent language, or how we perceive language, is through our vision system, at least text, written text. So we actually made the sentences come in just as the pixels of sentences. So the vision input is just a 256 by 32 sort of snippet of a sentence, and these are the convolutional layers. The audio input comes in, I think it was 8 hertz or 8,096 or something. So this must be like a 4-second audio snippet. We put them in together into sort of this kind of like the VQA architecture, where they come in and they have to go through this joint embedding. And again, sort of the idea of the joint embedding is, can this intermediate layer here represent both language, or in this case vision, and audio together? And then it has this auto-encoder structure where it comes in, it gets sort of embedded here, and then what you need to do is reconstruct the vision or the audio at the end. All right. Okay, so if you look at the convolutional elements here, so the filters of the vision, and these would sort of be the equivalent filters in the audio domain. They start off as white noise, completely random, and then this is what sort of emerges after you train it for a little bit. And at least in the vision, it makes sense because the filters that are trained start to look like letters, and then the filters that you see in the audio domain kind of sound like, I say they sound like phonies, but I don't know. It sounds like parts of real. Okay, so then if you look at the joint embedding, now it's hard to visualize. It's difficult to visualize what these things respond to. So what a different way of visualizing is, you take an input, the system, and then you see what neurons respond in a higher layer, and then you sort of some input triggers some neuron in the higher level very strongly. You can say, oh, then that neuron. You can weight that neuron as part of that input. It's called activity triggered averaging. So if it activates it, then you say, oh, this neuron responds to this input by some weighted sum. Okay, so then if you look at the embedding layer, this is what this is over the training. You can see most of the neurons don't really respond to anything particular, but there are some, like, you can't see back there, but this one is like look and pet and iPet, and so you can kind of start to see some words emerging here, which was interesting. But what was even more interesting is that if you look at, so imagine this is a neuron that's in the embedding layer, and it has seen input and it has heard input, and it's sort of not surprising that some sort of structure comes out. But if you look at what the neuron responds to in the visual domain, and then you look at what the same neuron responds to in the audio domain, they respond to the same thing, except in different modalities. And so this was just an accident that happened when we did sort of the architecture. And so I showed this to him. This was sort of early on. I was like, oh, that's interesting, right? He's like, oh my gosh, he found the Jennifer Aniston neuron. And I was like, what's the Jennifer Aniston neuron? Have you guys heard of this? Jennifer Aniston neuron? Okay. So So back in 2005, there were a bunch of neuroscientists that they wanted to explore something called the grandmother neuron. Well, actually, maybe they were just poking around people's heads. But so the idea of the grandmother neuron is that we have neurons in our brain, and so through a series of experiments, people have shown that at least in the visual cortex, neurons fire very specifically, very selectively to different stimuli. So there was Hubel and Wiesel. They looked at V1, which is the lower level of the cortex. They had neurons responding to diagonal elements and nothing else. And a neuron would respond to movement that sweeps to the right, whereas a different neuron would respond to movement that sweeps to the left. And then we have something called the fusiform face area within the brain that responds very selectively to faces. So what we know is that neurons are very selective. And so they went around and they wanted to see, well, can we find what stimulates some neurons? And so they put so they went to hospitals because obviously you need very precise measurements. You can't cut people's heads open, put probes in their brains, unless their brains are open already, which they found some epileptic patients where they had some severe epilepsy. They had to go under surgery. Their brains were already open, and they said, "Hey, can we just stick some probes in?" They said yes. And so there was this patient that they stuck some probes in, and then they just started showing them pictures, and it was measuring just one specific neuron, or it's maybe like a series of probes, a series of neurons. They were showing pictures, and it didn't respond to anything. So what you see here is the onset of the picture, and then the offset of the picture, and then the red bars would be the firing rates of that neuron. So something that is very excited by its input, it'll fire very, very rapidly. Okay, so it doesn't respond to anything except when they showed a picture of Jennifer Aniston. Just by accident, they showed a picture, and this neuron responded. So it responded very strongly to Jennifer Aniston. Said, "Oh, that's interesting." So they got a whole bunch of other pictures of Jennifer Aniston, and they kept showing, and it's responding to any sort of orientation or elimination of Jennifer Aniston. And then, interestingly, actually, when they had Jennifer Aniston with Brad Pitt, it sort of suppressed. They said, "Oh my gosh, it responds only to Jennifer Aniston." And so they went and they repeated this exact same experiment. So there's a different patient, different part of the brain, they showing pictures and stuff, and they found that this neuron responds to pictures of Halle Berry. So very strongly to Halle Berry. Even like a sketch of Halle Berry, it responded to that Halle Berry as Catwoman. And then in just the name, so like you show a picture of the name, responds very strong. So it's not like a face thing where it's like, oh, it has to be fitted. It's just the concept of Halle Berry made this neuron respond very strongly. Okay, so this is again from that paper where so these are different pictures of different people, and then if the red are pictures of Halle Berry, and the rest of these pictures, these responses are from different people, and you can see like, and so the last one here was just the name of Halle Berry, very strongly, number of spikes here. So why? So in fact, you can see like if you just did like a threshold of the spiking activity of that specific neuron, you could tell what the person's looking at. That person's looking at Halle Berry. So it's sort of a classification.
Did they show similar people like to Halle Berry?
Sorry?
Similar looking people to Halle Berry? Like that would have been someone.
I don't know. Like these, I can't really tell. The quality's not that great, but would be. yeah, no, I mean, it was definitely just
What about like hearing the name of the
yeah. So they didn't do that, but that would have been interesting to see it. It happens in the auditory.
So they were conscious of the.
Yeah. Their heads were open. Okay. So we accidentally, so while we were doing sort of this read to me sort of thing, we accidentally said we came across this in the embedding space where neurons seem to respond both to the image and to the audio. And so then we sort of changed direction and said, let's try to hone in and see if we can replicate this Halle-Berry neuron. So we chose Halle-Berry because, at least in the neuroscience experiment, they had showed the name of Halle-Berry, which was more interesting than just pictures of the face. So let's try to see if we can find it. And so what we did was we're going to use some principles of neuroscience, overarching principles of neuroscience that we believe happen in the brain for a purpose. First one is sparsity. So have you guys heard the saying, like, you only use 10% of your brain? That's not true. The reason I think the reason that came about was the fact if you were to measure the electrical activity at any one time of your brain, it's actually mostly silent. Right? So you can't have your brain, the neurons in your brain firing all the time. So they fire very selectively. We wanted to look at sparsity in because it's biologically plausible, as well as there are some very nice properties that come out of sparse vectors, sparse representations. So if you imagine you have, again, sort of the most sparse that you can be is that one hot vector, where you have just this corresponds to a certain word in the vocabulary. Well, if you then you see this one hot go off and you see another one over here, and you say, oh, okay, then I understand that means that it's the word Paris and it's the word run. So it sort of naturally disentangles information if it's sparse. You have this efficient variable size representation, and people have shown that it's actually more linearly separable if you have a sparse representation than a dense one. It has computational benefits. These days there's a lot of work in sparsifying these matrix vector multiplications. If you can get most of them to be 0, then you don't have to do any computation. So that's nice, and it's also neurologically plausible. Right, so we looked at, this is sort of an older data set, labeled faces in the wild. Yeah, like it was older than that, but maybe this was a revisit. Anyway, so if you look at the top most frequent people within this data set is George Bush, 530. Colin Powell came next. Donald Rumsfeld's again political figures. And Halle-Berry was there like 12 times in the data set. But of course, we're like, we need to augment the number of images of Halle-Berry, so we scraped the internet tirelessly, and increased the number of faces of Halle-Berry in this data set to be second. So we didn't want her to be, the most popular in the data set, just to make sure we didn't get any sort of weird effects. So George Bush is still number 1. And we wanted to make sure that we had sort of this control that does it have anything to do with the fact that we're putting these elements like lateral inhibition or sparsity within a network? What if we just do a straightforward deep multimodal deep autoencoder from, like, this was TensorFlow with Keras. So we had the exact same architecture of an autoencoder built, this was Keras at the time, and then we have our corresponding architecture. It's the exact same, except what we have is we're doing sparse coding here. Yeah, that's right. We're doing sparse coding to do these layers, to sort of get the representations of these layers. Sparse coding, and I'll talk about this, but it has, if you imagine deep learning as sort of one layer to the next layer to the next layer, if you look at the nodes within the layers in a deep learning model, there's no connections between them. So what we have is we have lateral connections within the layers. So all the nodes are connected to all of the other nodes within the layer. And then we also have this element of top-down feedback, which, again, you don't see this idea of top-down feedback within a deep learning model. You may sort of, an argument that you can make is that top-down feedback in a deep learning model is the backpropagation of supervised learning. But my counter argument to that is that at the time of inference, at the time when you deploy your model and some input comes, in a deep learning model, typically the input comes and it goes to the output, and there is no feedback in that loop, right? It's just feed forward. Whereas what we're saying is, yes, fine, you can sort of tune your weights to backpropagation. It's sort of a offline top-down feedback. But during inference, if I see something or hear something, not only am I going to be influenced by sort of the weights of the network, but there's some sort of expectation that our brains have, or that this network has, that is also being pushed down at the same time, right? So you can imagine. So I'll show you how we play with this, but in this case, you can imagine like if you have conflicting inputs. So have you heard the McGurk effect, where you're watching someone's lips move, and then you have a sound. Maybe it's like a phoneme or something. And depending on what you hear, it's going to change the way you see how their lips are moving, or vice versa. So there's definitely sort of this influence of top-down feedback that we have in perception at inference time that we wanted to model. All right. This is the sparse coding problem, where we're going to have some input come into the image, or input to the network. So this is like an image. And then all we're trying to do is minimize the difference between this input and a reconstruction of that input. So this phi A is, you can imagine this is a dictionary. In the case of the read-to-me stuff, this would be, the dictionary would be those letter-like things that emerge, or the audio sort of phonemes that come out. And it's going to be a linear combination of so these would be the coefficients, the activity of those dictionary elements, in order to reconstruct that. And so we're going to penalize this reconstruction by an L1 regularization here, which says that what we want is most of these elements to be 0. So we only want to use a few of these dictionary elements to do the reconstruction. And if you kind of look at the literature, I think there's confusion between like a sparse autoencoder versus sparse coding. So when you sort of look at the typical autoencoder, like you can do this within a deep learning library, and it's almost always about dimensionality reduction, which makes a lot of sense in most cases, where again you have your input and you're trying to reconstruct your input, the reconstruction, and you're going to pass it through sort of a lower dimensional space. You want to encode it sort of compress it in this space. So the idea would be these nodes would encode all of the information that you need in order to do this reconstruction. Whereas when we're talking about sparse coding, this is more of the picture that I have in my mind. You have an input, you have an output, but the hidden layer between the input and output is going to be a dimensionality expansion. So but the sparsity penalty is going to enforce that only a few of these. So it's still sort of reducing the encoding into a lower dimensional space, but it has much more flexibility to do so. Yeah.
Because I wasn't here, I'm sorry if you explained it earlier. Well, how's the input? Is it at pixel level?
Yeah, so we're gonna do, at least with the images, we have the pixels coming in, but just like convolutional neural nets use like filters, filter responses, we're gonna do this. And same with audio. Audio, the input was the raw audio signal, but then we have the one-dimensional convolution. Okay, and let's see. Okay, so there was a paper in 2008 from this guy Rizal, and I think at the time he was either a postdoc or PhD student with Bruno Mulshausen, who came up with all this sort of sparse coding framework. He said, well, we can solve this sparse coding problem as an energy minimization problem, just sort of reformulate it, where, and I'm not gonna go into this, but basically you can drive. Okay, so the whole idea was, can we sort of map the energy minimization to biological semantics? And so the first thing is that neurons, they're cells, and all cells have membranes. And the special thing about neuron membranes is that they can hold a voltage or electrical charge. And so we can talk about the membrane potential of a neuron. So what we're going to say is all neurons have this sort of dotted line. The dotted line is going to be the membrane potential. So some sort of electrical voltage. Now, what happens is if the voltage goes above a certain threshold, or maybe it's below, no, it's negative, but then if it goes above a certain threshold, then it will fire that neuron, and sort of the signal will propagate. So connected neurons. In this case, we have a membrane potential. We're going to define a threshold for this. So U is going to be this membrane potential. We define a threshold. If U crosses the threshold, then it's going to fire. And we can say then the activity or the coefficients of that dictionary element are going to be non-zero at that point. And so if you take the derivative of the energy with respect to this activity, what you sort of get is this interesting interplay. So what happens is the membrane potential of the neuron is going to drive the potential up. And this is the image patch. So this is the input image, and this is going to be the filters, or the kernel elements of the convolutional kernel elements. Now, this is the dot product between them. So if the filter matches the input, so if it's like a diagonal and a diagonal filter, if they match, if they align well, then it's going to drive up the membrane potential very strongly. Okay. So this is essentially the driver of the membrane potential, and then we have inhibition coming out of this as well. So what's going to happen is if this is being driven up by the input image, we're going to have inhibition coming from every other neuron in that layer. So it's going to say, no, I'll push you back down. So if this neuron, this is the one we're looking at, but if this neuron has fired already, then I'm going to inhibit you from firing. And I'm going to inhibit you by the proportion, again, it's the dot product of my image filter and your image filter. So this is a diagonal, and this is like a circle. Even though the circle fired, it won't inhibit me as much because we don't match the circle diagonal. But if this diagonal fires, and this diagonal is being charged up, and this one already fired, it's like a winner take all. It says, no, I'm taking this, and it's going to inhibit you from firing proportional again to the dot product. All right, so just to make this sort of concrete, this is a pretty bad example, but it's the best that I have. If I'm trying to reconstruct this, I'm trying to sparse code this, and these are my dictionary elements. So I need some coefficients of these to reconstruct this. You can see that I would take 0 of these because I don't need these to reconstruct that. These actually look pretty similar, so I'll take some non-zero portion of these and then 0 of them. And so what you're going to see here is this is going to be the membrane potential. This is going to be the activity. So if it crosses this threshold, then they'll become active. And so 6 is this one. It takes the representation here, and as 6 goes up, what it's doing, 6 crosses, it's going to inhibit all the other ones. So 5, 7, 5. So they actually start to go down. The next thing that we add to the network is something called top-down feedback. And it's been shown that people have shown that like what you see, perception, they would say is like a controlled hallucination, which I think is interesting. So it's not only what comes in, but also your expectation of what you see. And I get this a lot at home because my wife is always like, bring me the milk or something. And I open the fridge and it's like right in front of my face. And I'm like, I don't see the milk because I don't expect to see it in the place that's new or whatever. So anyway, so what we have is this idea of top-down feedback where we have some expected. You have something expected to be seen, and it's going to push. So this is going to be top-down. It's going to suppress the neurons at the lower layer that are not consistent with expectation. In this case here, there is no expectation coming back down. This is just input coming up, and then actually there's a little bit, because if you think about the receptive, the scale of what the lower level sees, it sees like these little image patches, and then at the higher level it has sort of a broader view. It might see the whole image or something like that. And so the smaller, the lower level would try to represent this image patch in a certain way. Maybe it uses like these diagonals that belong to houses. But at the top level, it says, no, this is an airplane. Stop using sort of the house neuron. But if that's not clear, I have an example that is clear. Okay, so what we did was we had, again, sort of a very basic neural network here where we have paired handwritten digits, B's and 13s, with the type-based. So there's no ambiguity over here with the type-based, but we purposely made these B's and 13s sort of difficult to decipher. Right? And then, so we train them together, and then we take one of the arms away. Right? So we don't put in the type-based anymore. And if you were to look at this is the test input. What do you think it is? A B or a 13? B.
B.
Yeah, most people say it's a B. And the neural network, actually, if you look at so you sparse code this, it has some sparse vector representation, and we take all of the training, and we find the cluster centers of the B's and the 13s. At this level, it's right in the middle, so it's not short. But if you look at the L2 distance between cluster centers, it says it's closer to the B. And if you look at the top level here, it's right smack in the middle of the B's. So it's actually pretty sure that it's a B. Now what we do is we add, so it originally it thought it was a B, and then we add 13 on the other side. Right? So now we're saying, no, you're wrong. This is actually a 13. So this representation obviously is 13. The top layer here is called P1. P1 sees both the handwritten and the typeface, and it clearly changes its mind. Right? It says, no, you're absolutely right. This is a 13. So the representation moves all the way over to almost the cluster center of the 13s. But I think what's really interesting is that here. So originally it was ambiguous. It was sort of undecided, but it was still closer to the B cluster center. And then when we add the 13, this has to sparse code both of them, and then this one's going to push down expectation. So this is how we introduce what you're expected to see to the lower layer, and the lower layer is going to actually change. It's going to inhibit the neurons that respond to B's and only use the neurons that respond to 13s. So you can see it actually shifts its representation over to 13. Okay, so this was probably the most exciting thing that result. Okay, so we then did this. So we compared the two, and we were doing this on Halle images versus just random images. And this is what happens in a sparse autoencoder. So we added just L1 sparsity to a standard convolutional autoencoder. And what you see coming out of the responses is more like a PCA of reconstruction. So it actually doesn't care if a Halle Berry image comes in or a random image comes in. It just uses all the components of sort of maximal variation and can reconstruct. Whereas if you look at the sparse coding model, what happens is if you look at an average over 75 images, no one of these is very strongly activated, whereas in every single image and every single text of Halle Berry that we put in, we have this really strong response in Neuron 326. And so Neuron 326, if we look at it further, then any image that comes in that's not Halle Berry doesn't actually activate this very strongly. With all of the faces of Halle Berry activate this, as well as the text. So if you see with the responses to text, then Halle Berry is very strong. The image only, the text only. You can see that the text never changes, but the membrane rent. This should be. This is not quite. Right. If you look at the activity triggered averages of the neurons over time in that joint embedding layer, this is what they respond to, and I think in the same way. This is what the text responds to. And what you have is that you have these invariant neurons emerging where some respond. This is 326. This one's very strongly in a Halle space or the text. And then you also have other invariant neurons coming out of the training examples that happen most frequently. All right, so running out of time, but what can you do with this? You can do generation. So here, imagine you just put vision, or you just put text, or you just put audio in, and you pass it through here. Because these neurons are invariant to what they respond to, you should be able to get the same vector representation and then generate the missing modality. Whereas what's interesting that happens in a deep learning autoencoder is that the joint embedding, it learns how to split this representation. So let's say you put vision and you put like audio in, it's going to say, all right, there's no explicit objective for me to sort of merge my representations. In fact, what I'll do is I'll just split this in half, and I'll just use half the neurons to encode the vision and half the neurons to encode the audio. So with the sparsity penalty, we're forcing neurons to be very selective. What we see is, so this is generation. So it's actually kind of weird because we generate this gibberish, but if we sparse code it again, it certainly is. And then this is the generation out of the deep learning model. And this is the generation out of the sparse code. So it actually, I don't know what happened here, but it actually looks a lot more like the image. And then this was sort of a joke that we put in at the very last figure of the image of the paper, where we put in Halle Berry as a Catwoman, and this is Neuron 326. It just so happened to respond better than these images of Catwoman. But if you put other images of Catwoman, then it actually just doesn't hold. This was supposed to be a joke, but no one actually got it. All right, so that's, I think I'm running out of time, but are there any questions?
So you mentioned the grandmother neuron?
Yeah.
What is that?
So the grandmother neuron, this is back in like, I don't know how old that is, but the theory was that, again, sort of, people knew that neurons in the brain fire very selectively to different stimuli. And the theory was that as you interact with someone, more and more, so someone you interact with very frequently, your brain is going to associate a neuron to that person. So it's called sort of grandmother. Now we know that's not true, but what we do know, I think we can say, is that it's not a single neuron. So if you were to lose that neuron, then you don't know your grandmother anymore. So it's not a single neuron, but it's like a sparse population.
Question about the representation. How did you pass the intermediate level understanding of your model? Like, are they the weights or
You mean
text and
like
images?
like this stuff?
No, like previous slide, I think. Like the images.
Oh, the activity triggered
Yeah.
outcomes.
Yeah, it is.
So
Backtrack.
I tried to explain this, but I think I did it poorly. So in the embed, so you have a layer, and you have the activity of the neurons in that layer. And so if you put an image in, and you see, like, let's say it's like 1,000 neurons, and you put an image in, and you just look at the activity at a higher level. Let's say like 326 is really high. So then you can say, oh, this neuron responds to this input image in this way, this response. And then for every neuron, you can say, like, if I want to know what 326 responds to, then I'll take that image and I'll weight it by the activity. And then I take another input image and I see what is the the activity of 326, and it's probably lower. And so then I add this input image plus this input image according to the weight of their response. And so if you just do it over the whole training set, then it's going to be a weighted average of essentially how that neuron responds. All right. Great. So that's it. I think next week, okay. Did you send me a paper or? You did send me a paper, right?
Yeah.
Okay. Let me look it up and I'll send it around.
Oh, thank you.
And yeah, thanks.